All right, welcome. Have you ever actually stopped to wonder what's going on under the hood when you send data across a network? Like, how long does it really take? Well, today, we're going to dig into that exact question. We're going to calculate the total time it takes for data to get from point A to point B right through a switch. Let's jump in.
Okay, so here's our challenge for today. We've got two computers. They're connected by a packet switch sitting in the middle, and we need to send a 10,000-bit chunk of data. Sounds pretty straightforward, right? Well, as you're about to see, there are a few different kinds of delays that we have to factor in to get the correct answer.
So, these are the tools we get to play with. The problem lays out all the variables we're going to need. First off, our 10,000 bits of data get broken down into two packets, each 5,000 bits in size. We've got a link speed, a propagation delay, that's basically travel time, and a processing delay for the thinking time inside the switch. And here's a really key detail. The switch uses a store and forward method. Trust me, that's going to be super important in just a minute.
You know, the best way to solve a problem like this is to just tell a story. So that's what we're going to do. We are going to follow the very first packet on its entire journey, from the second it leaves the first computer until it lands safely at its destination. Let's track every single step.
Okay, so the very first delay our packet hits is called transmission delay. I want you to think of the network link like a highway, and our packet is a long line of cars. The transmission delay is just the time it takes to get that entire line of cars off the on-ramp and onto the highway. So naturally, it depends on how big the packet is, how many cars, and the link rate, which is how fast you can get them on there.
So, for our problem, we take the packet size, 5,000 bits, and we divide it by the link rate, which is 1 million bits per second. And that gives us our first delay, 5 milliseconds. Easy enough.
Next up, we've got propagation delay. So once a bit is actually on the highway, this is the time it takes to physically travel from one end of the wire to the other. This one has nothing to do with the packet's size. It's all about the physical distance it has to cover.
Now the problem is nice and just gives us this number, 20 microseconds. To make all our math easier, we're going to keep our units consistent. So let's just call that 0.02 milliseconds. It's a tiny amount of time, but you'll see it all adds up.
And this brings us to a really important concept that honestly trips up a lot of people when they're first learning this stuff. You have to remember, transmission delay is the time it takes to push the packet onto the wire. Propagation delay is the time it takes for the bits to travel across that wire. They are two totally different things, and you can't mix them up.
So, let's put together the first leg of our packet's journey. It takes 5 milliseconds to transmit, or push, the packet onto the link. Then, it takes another 0.02 milliseconds for it to propagate or travel across it. This means the very last bit of our packet shows up at the switch 5.02 milliseconds after the whole thing started.
Okay, our packet has arrived at the switch. But the switch doesn't just instantly shoot it out the other side. Nope, it's got to do a little bit of work first. We call that the processing delay. It has to look at the packet's header, maybe check for errors, and figure out which wire to send it out on. And this is where that store and forward thing comes in. It means the switch has to receive the entire packet, all 5,000 bits, before it can even start doing this processing work. So let's map out the entire trip now. We've got the transmission and propagation on that first link to the switch. Then the switch takes its 35 microseconds, which is 0.035 milliseconds, to process it. And then the whole thing starts all over again for the second link. Another 5 milliseconds of transmission to get it onto the second wire, and another 0.02 milliseconds of propagation to cross it to the final destination.
So if you put it all together, the full equation for our very first packet's journey looks like this. We're literally just adding up every single little delay that it hit along the way, from the source through the switch all the way to the destination.
Add all that up, and you get a total journey time for our first packet of 10.075 milliseconds. But, and this is a big but, we're not done yet. Remember, we sent 2 packets.
So, the obvious question is, do we just multiply that number by 2? It seems logical, right? But nope, that's not how efficient networks work. The key here is something called pipelining. The network is smart. It doesn't just sit around and wait for the first packet to finish its entire trip before starting on the next one.
And this is where you can really see the magic of pipelining in action. Just look at this timeline. At the 5 millisecond mark, the very instant the source computer finishes pushing packet 1 onto the wire, it immediately starts pushing packet 2. The two processes totally overlap. By the time packet 1 finally arrives at the destination, packet 2 is already well on its way, hot on its heels.
And this little overlap reveals a really cool shortcut. Because these packets are sent back to back,
The second packet is essentially just trailing the first one. It's going to arrive at the final destination exactly one transmission delay after the first one does. All that other travel and processing time is already accounted for in that first packet's journey.
So this makes our final calculation way simpler. The total time for all the data to arrive is just the total time it took for that very first packet to make its complete journey, plus one extra transmission delay for the second packet to get pushed out from the switch right behind it.
So we take our 10.075 milliseconds for packet number 1, we add that 5 millisecond transmission delay for packet number 2, and we get our final answer, 15.075 milliseconds. That is the exact moment that the very last bit of the very last packet arrives at the destination.
So let's quickly recap the big ideas here. First, store and forward is a critical rule. The switch has to swallow the whole packet before it can spit it back out. Second, that pipelining trick is a huge time saver. It lets the network multitask. And finally, the total time really comes down to the full journey of that first Trailblazer packet, plus just the transmission times of all the packets that follow.
And that brings us to a final little brain teaser. Everything we just did was for a store and forward switch. But what if it was a cut-through switch? Those are faster. They can start sending a packet out the door the moment they've read the destination address without waiting for the whole thing to arrive. So how would that change our final answer? Something for you to chew on. Thanks for joining me.